The root test, sometimes you could choose between the ratio test and the root test for some of these problems, but to use the root test for this, we got a sequence here. We're going to turn it into a series by adding from n equals 1 to infinity. So to evaluate this series and whether it's convergent, we want to evaluate the limit as n goes to infinity for the nth root, the absolute value of a sub n. So that's the limit as n goes to infinity of the absolute value of n to the power of e, so it's got a constant for power, over e to the nth power, and then this is, you could write that as to the power of 1 over n instead of the nth root. Let's see, so n is going towards positive infinity. That means we're not going to have any negative values in here, so we could just forget about the absolute value, right? Let's see, I think that's all the other simplifying we can do before we start applying the 1 over nth power. So a power on top of another power that would multiply, so we're evaluating the limit as n goes to infinity of n to the e over n power over, now 1 over n times this n up here just leaves us with e, so we just have a constant. And now we can evaluate this limit. This is just a constant on bottom, so you could factor out a 1 over e from the limit. So as n goes to infinity, we're dividing by a bigger and bigger number. So this fraction here is getting smaller and smaller and smaller, right? It's getting close, it's tending towards 0. But we also are dividing by n that's going towards infinity. So it looks like, what can we do here? It's an indeterminate limit because we have the limit as n goes to infinity of something going towards infinity to the power of something going towards 0. So like infinity isn't a number. We can't just say infinity to the 0 power. So usually what we do when it's indeterminate is we try to write it with L'Hopital's rule. But L'Hopital's rule works when you have some function divided by another function. We don't have a fraction going on in here. But I think we could rework with logarithms. So this is 1 over e, valuing the limit as n goes to infinity. So you could use whatever base of logarithm you want. So let's just use, I guess we have e going on anyway. So let's use e to the power of natural log n e over n. Right, this is the same thing because e to the power of natural log, that would cancel out and leave us with just n to the e over n power. But I think it's going to help us because now if we use the exponent rule of logarithms, we can factor out this e to the power of e over n times natural log of n. So now we could write it as a fraction in the numerator, something that we could use L'Hopital's rule on. So this would be e, let's say e to the power of e times e to the power of natural log n over n. So this is something we could apply L'Hopital's rule with because this doesn't involve n, so we can just evaluate the limit as n goes to infinity. That's one of our early logarithm properties in calculus. So when we're evaluating that limit of as n goes to infinity of the fraction that's in the exponent, then we can apply L'Hopital's rule, evaluate the derivative of the numerator and the denominator. Running out of room everywhere. Let's factor out. Something doesn't feel right about that. E to the power of e. Oh, because it's not right. That would mean that we'd be adding these. I messed something up here, so we got to keep the e over here. So we can forget that step, sorry, because that would be e to the power of e times e to all this stuff. That would mean we'd be adding the e's, but e is a coefficient, easy multiplying, so I got to keep it there. But using our rules of limits, we can evaluate the limit as n goes to infinity of this fraction. just going to write limit to save. Here, actually, we can put limit in the numerator. So this is what we're evaluating. E to the power of the limit of n goes to infinity of this fraction, e times natural log n over n. And that's what we're going to apply L'Hopital's rule to. So the derivative of the numerator, derivative of natural log of n, that's 1 over n. And the derivative of the denominator is just 1. And we're still evaluating the limit, but now that's a limit that we can evaluate, right? This is 1 over e times e to the power of the limit as n goes to infinity of this term is going to be 0 because this goes towards 0 as n goes to infinity, and 0 times e makes 0. Holy cow, the whole thing simplifies just to be 1 over e to the first. That's the limit we were asked to evaluate. Okay, and so the important part here is that if the limit is less than 1, then we have something that converges. If the limit is greater than 1, then it diverges. So if you divide 1 by e, e is 2 point something something, right? So that's definitely less than 1. So we could say that this series converges by the root test.